Welcome back. In the previous lesson, we introduced the fundamental idea of descriptive geometry by learning how to project a single point onto the principal planes of projection. Although a point is the simplest geometric element, engineering drawings are rarely made from individual points alone. Mechanical components, buildings, bridges, machine parts, and structural frames are all constructed from straight edges. Every straight edge that we see in these objects is represented by a straight line. Therefore, before we can project complete engineering objects, we must first understand how to project a straight line accurately. In this lesson, we begin with the two simplest positions of a straight line: a line parallel to the horizontal plane and a line parallel to the vertical plane. While these cases may appear straightforward, they introduce one of the most important concepts in engineering drawing: the difference between the true length of a line and its apparent length after projection. Once this concept is clear, the projection of inclined lines and more complex engineering problems becomes much easier to understand. Let's begin. Welcome back. In the previous lesson, we learned how to project a single point onto the principal planes of projection. A point is the most fundamental geometric element in engineering drawing. Now consider 2 points, A and B. Joining these 2 points produces a straight line. Machine components, buildings, bridges, and engineering structures are all made from straight edges. Although these objects appear very different, every one of them is built from straight lines. Therefore, before learning how to project complete engineering objects, we must first learn how to project a single straight line accurately. A straight line is completely defined by its 2 endpoints. Once we know how to project these endpoints, projecting the entire line becomes straightforward. Now, let us learn how a straight line is projected onto the principal planes of projection. Here are the 2 principal planes of projection: the vertical plane standing at the back and the horizontal plane lying below. Together, they form the first quadrant. Any object placed in this quadrant between the observer and the planes is drawn in first angle projection, the convention we follow throughout this course. Consider an arbitrary straight line joining points A and B. The first step is to project point A onto the vertical plane and the horizontal plane. Repeat the same procedure for point B. Finally, join the corresponding projections of the 2 endpoints. Joining the front projections gives the front view, while joining the top projections gives the top view of the line. This simple procedure applies to every problem involving the projection of straight lines, regardless of their orientation. Now, the appearance of the projections depends upon the orientation of the straight line with respect to the principal planes of projection. Let us begin with the simplest possible position. Consider a straight line joining points A and B, placed in the first quadrant, above the horizontal plane and in front of the vertical plane, as required by first angle projection. Observe that both endpoints are at the same height above the horizontal plane. Since every point on the line is at the same height above the horizontal plane, the line is parallel to the horizontal plane. Now observe the distance of the line from the vertical plane. Notice that every point is also at the same distance from the vertical plane. Therefore, the line is parallel to the vertical plane as well. This is the simplest orientation of a straight line. It is parallel to both the horizontal plane and the vertical plane. The next step is to construct its orthographic projections. Before we do that, try to predict what its front view and top view will look like. The appearance of in the previous scene, we established the position of the straight line. The line AB, 60 millimeters long, is parallel to both the horizontal plane and the vertical plane. Let us now construct its orthographic projections. We shall first construct the front view of the line. Draw a projector from point A perpendicular to the vertical plane. The point where the projector meets the vertical plane gives the front projection of point A, denoted by a prime. Similarly, draw a projector from point B to the vertical plane. The point where the projector meets the vertical plane gives the front projection B prime. Join the front projections A prime and B prime. The resulting line represents the front view of the straight line. Next, we shall construct the top view of the line. Draw a projector vertically downward from point A onto the horizontal plane. The point where the projector meets the horizontal plane gives the top projection of point A, denoted by small a. Repeat the same procedure for point B. The point where the projector meets the horizontal plane gives the top projection, denoted by small b. Join the top projections A and B. The resulting line represents the top view of the straight line. The construction is now complete. We have obtained the front view and the top view of the straight line. In the previous scene, we constructed the front view and the top view of the straight line. Let us now examine these projections and compare them with the original line. We now have three lines before us. The original line in space, its front view on the vertical plane, and its top view on the horizontal plane. Let us first compare the original line with its front view. The given straight line has a length of 60 millimeters. Notice that the front view has exactly the same length as the original line. Therefore, the front view preserves the actual length of the line. Hence, the front view represents the true length of the straight line. Let us now compare the original line with its top view. The top view also measures 60 millimeters, exactly equal to the length of the original line. Therefore, the top view also preserves the actual length of the line. Hence, the top view also represents the true length of the straight line. Both the front view and the top view have preserved the actual length of the original line. So far, this picture lives in three-dimensional space, but an engineering drawing must live on a flat sheet of paper. Watch how we get there. First, set the original line aside. Its job is done, and keep only the two views resting on their planes. Now the key move. The vertical plane already stands in the plane of the paper, so hold it still. Rotate the horizontal plane about the XY line, swinging its front edge downward toward you, and the top view rides along with it. This is the first angle convention. The front view sits above the XY line, and the top view sits below it. Both planes now lie in one single flat plane. Let us look at it exactly the way you look at your drawing sheet, straight on. Merge the two planes, and together they become one thing, the drawing sheet with the reference line XY running across it. And on paper, the two views become what they truly are, crisp pen lines. Label it like a worksheet, a dash, B dash above XY, the front view, and a B below XY, the top view. And notice, a dash and a stand on one common vertical projector, and so do B dash and B. Corresponding views always align. Now dimension it exactly as you would on paper. The front view, a dash, B dash, measures the full 60 millimeters, the true length of the line. The front view stands exactly 30 millimeters above XY, because the line in space was 30 millimeters above the horizontal plane. Height above HB becomes height above XY. In the top view, AB lies 25 millimeters below XY, because the line was 25 millimeters in front of the vertical plane. Distance from VP becomes distance below XY. Every number from space lands unchanged on the flat sheet. We can now summarize our observations. Both the front view and the top view have the same length as the original line. This is the simplest position of a straight line and serves as the foundation for understanding all other orientations. Therefore, whenever a straight line is parallel to both the horizontal plane and the vertical plane, both the front view and the top view represent the true length of the line. In the previous scene, let us now consider another important orientation of a straight line. Consider a straight line AB, 60 millimeters long, again placed in the first quadrant, above the horizontal plane and in front of the vertical plane. The actual length of the line is 60 millimeters. Observe that the line stands vertically above the horizontal plane. Therefore, it is perpendicular to the horizontal plane. At the same time, The line remains parallel to the vertical plane because every point on the line is at the same perpendicular distance from the vertical plane. This is our second special position of a straight line. In the next scene, we shall construct its front view and top view. In the previous scene, we established that the straight line AB is perpendicular to the horizontal plane and parallel to the vertical plane. Let us now construct its orthographic projections. We shall first construct the front view, followed by the top view of the straight line. We shall begin by constructing the front view of the straight line. Draw a projector from point A perpendicular to the vertical plane. The point where the projector meets the vertical plane gives the front projection of point A, denoted by a prime. Similarly, draw a projector from point B to the vertical plane. The point where the projector meets the vertical plane gives the front projection of point B, denoted by B prime. Join the front projections A prime and B prime. The resulting line represents the front view of the straight line. The front view of the straight line has now been obtained. Next, let us construct the top view of the straight line. Draw a projector vertically downward from point A onto the horizontal plane. The point where the projector meets the horizontal plane gives the top projection of point A, denoted by small a. Now project point B onto the horizontal plane. Notice that the projection of point B falls exactly on the projection of point A. The top view of the straight line has now been obtained. In the previous scene, we constructed the front view and the top view of the straight line. Let us now examine these projections and understand what they represent. We now have the original line, its front view on the vertical plane, and its top view on the horizontal plane. Let us first compare the original line with its front view. The original line has a length of 60 millimeters. Notice that the front view also measures 60 millimeters, exactly equal to the length of the original line. Therefore, the front view represents the true length of the straight line. Let us now examine the top view of the straight line. Unlike the front view, the top view is represented by only a single point. Notice that the projections of both endpoints fall exactly on the same point of the horizontal plane. Since the line is perpendicular to the horizontal plane, all points of the line project onto the same point. Therefore, the top view is called the point view of the line. This picture still lives in space. Let's convert it into the flat worksheet drawing. Set the original line aside and keep only the two views resting on their planes. Hold the vertical plane still and rotate the horizontal plane about the XY line. Its front edge swings down toward you, carrying the point view along with it. As always in first angle projection, the front view lands above the XY line and the top view below it. Everything is now flat. Look at it straight on, exactly like your drawing sheet. The two planes merge into one flat surface, the drawing sheet, with the reference line XY across it. On paper, the views become crisp pen marks, a line, and a single point. Label the worksheet. The front view is the vertical line, a dash B dash. The top view is the single point below XY. We write B first and in brackets because looking from above, B is nearer to the observer and A is hidden directly beneath it. And the point view sits precisely on the vertical projector through the front view. Views always align. Dimension it. The front view measures the full 60 millimeters, the true length of the line. The lower end of dash stands 10 millimeters above XY, the height of point A above the horizontal plane. And the point view lies 25 millimeters below XY, the distance of the line in front of the vertical plane. Length, height, and distance. Every given number of the problem now sits, fully dimensioned, on a flat sheet. We can now summarize our observations. The front view preserves the true length of the line, whereas the top view is represented by a single point. This is the second fundamental position of a straight line and forms the basis for understanding more complex orientations. Therefore, whenever a straight line is perpendicular to the horizontal plane and parallel to the vertical plane, its front view represents the true length of the line, while its top view is reduced to a point called the point view. In the previous scene,